This is lesson number 1 for the radical unit, simplifying radicals. The symbol on your screen is called a radical. A lot of you refer to it as a square root, and it is when it's assumed that you're talking about undoing a square. So square root, radical, that check mark thing right there, though, is called a radical. Sometimes when we use radicals or square roots here, they come out pretty. They're referred to as perfect squares. Others don't come out pretty. If you were to take the square root of 2, the square root of 15, the square root of 120, you'd get a decimal. So these ones don't come out so pretty. So these are referred to as irrational numbers because the decimal that you get doesn't end and doesn't repeat. What we're trying to do and the goal is to get our square root or our radicals down to perfect, simplest radical form. If you think about a fraction, for instance, 3 over 6, you were taught how to simplify fractions at a particularly young age. Your calculator can handle it for you. However, square roots, all you guys know right now is how to type it in, and that's no longer going to work. We want to get a square root down to its most simple form, but its non-decimal form. That happens when you meet one of 3 or all of 3 criteria. The idea is that you have no perfect square factors in the radicand, meaning you have no perfect squares under the square root. So look at an example of that one. The square root of 8. What numbers make up 8? 4 and 2. So the square root of 8 is really 4 times 2. It's not in its simplest form because it has a square root, it has a perfect square inside of it. We want no fractions inside the radicand, meaning we want no fractions underneath the square root. So if we had the fraction of 4 over 8, inside the radical would not be in simplest radical form. We want to make sure that there are no radicals in the denominator. An example of that. Not in simplest radical form because there appears to be a radical in the denominator. Lastly, please note, I probably shouldn't have made it quite so small, these aren't decimals. This isn't you typing your calculator and grabbing the square root of 8 and typing and writing down the decimal. This is us getting the square root down to its simplest non-decimal form. Just like 3 over 6 can be reduced to 1 over half. If I talk about keeping it as a fraction, it'd be 1 over half, not 0.5. Again, there's kind of an example with fractions, but we're still dealing with no decimals. Your luck will be greatly increased with this unit if you can remember your perfect squares. If you're in my classroom, they're over the chalkboard. I recommend recognizing the first 15. Continuing on, the method that we're going to use, and there is one other, but I'm just going to teach you one, is referred to as prime factorization method. For prime factorization, we first have to know how to get things down to their prime factors. Prime factorization is when you break down a number into the numbers that multiply to make it, not including 1. So you're getting the numbers down as small as they can possibly go. 48 is 8 and 6. 8 goes down to 4 and 2. 4 goes down to 2 and 2. 6 goes down to 3 and 2. So your prime factors would be those. Think about, for instance, the prime factors of 18. You can start with any numbers that make 18. I'll start with 6 and 3. 6 is made up of 2 and 3. So the prime factors of 18 are 2 and 3 and 3. If you wanted to try using prime factorization for 18 and starting with 9, you still end up with the same factors as you would have if you would have started with different numbers. So starting with 6 and 3 or starting with 9 and 2, our prime factors are still 2, 3, and 3, or 3 and 3 and 2, but it's the same idea. So the method that we're using, prime factorization. For this method, you need to break down the number into its smallest pieces. What you're going to do is break it down and then list all of them in the radicand. So the square root of 45 breaks down into, get a smaller pen, breaks down into 9 and 5, 3 and 3. So I listed 3 times 3 times 5 because those are the prime factors. At the beginning I mentioned that this symbol is called a radicand, or a radical. We very often know it as a square root, and the reason behind it is, if you wanted to undo a square, how would you do that? You learned in Algebra 1, or maybe even before that to undo a square, you use a square root. There is technically a little teeny tiny 2 in here called an index. It's actually right here. And it's that allows us to know that we're talking about a square root, as opposed to a cube root, or as opposed to a fourth root or a fifth root or something else. So when there's no value written in front of that square root or that radical symbol, that really means that we're talking about a square root. If you think about the idea of undoing a square, think about what a square is. If I talk about x squared, well, that's really me discussing x times x. I'm going through all of this because when you're dealing with prime factorization method, you're looking for pairs of factors. You're looking for two factors because when you talk about squaring something, it's two things. So look at your prime factorization, and I notice in 45 I have one pair of 3's. The value that makes that pair comes out in front, and it doesn't have the square root over it anymore. It's not square. What that means is that I have one pair of 3's, but the 5 didn't have a pair, so it stayed inside. Think about way back to preschool or kindergarten. You had to have the buddy system, like, hey, can I go to the bathroom? Sure, but you need to grab a buddy. This 3 has a buddy. It's identical buddy. So they can leave the square root, they can leave the classroom, and the 5 stuck inside because he doesn't have a friend. We're going to do quite a few of these. Kind of bear with me for a second. I know it takes a minute to get your brain wrapped around it. But check this out. In this yellow box, it says type each into your calculator. The decimal equivalents are the same. Just like 3/6 is the same as 1/2. They both equal the decimal 0.5. If you were to type in your calculator the square root of 45, look at its decimal. Now in your calculator type 3 square root 5. If you did it correctly, the decimal should be the same. All we're doing is breaking it down into its simplest non-decimal form. Last word to the wise here, that plain number, this 3 comes out in front because it's representative of the idea that you had one pair of 3's. I have a website here. I'd like to show you that in class. I think it'll make more sense. All right, some properties of radicals. Write this down. It's already on your paper. Properties of radicals, we can multiply them but not add them. We can divide them but not subtract them. Won't really come into play today. All right, lots of simplifying practice. Each time I'm going to break down these numbers into their prime factorization. I might start with a particular set of factors and break it down. You can start with another pair of factors and break it down. Ideally, prime factorization means we're all going to get to the same spot. So for 50, I think of 50 as 5 and 10. 5 can't break down any further, but 10 breaks down into 5 and 2, meaning the factors are 5 and 5 and 2. Because we're talking about square roots and undoing squares, we're finding pairs of numbers. I see one pair of 5's. 5, if you want to put that you have one pair, fine. Square root 2. Letter B, 18. Mentioned this on the previous slide, but we're going to do it again here. I'm going to factor 18. 9 and 2. 9 breaks down to 3 and 3. 3 times 2 are my prime factors. Look at all those numbers. Do you see any pairs? I see one pair of 3's. It's going to come out, and I have a leftover 2. How many pairs of 3's do you have? I only have one pair of 3's. 3 to the first power is 2. Or I'm sorry, 3 to the first power is 3. You don't technically need those ones, but some students like them there. Letter C. Square root of 48. I'm going to break it down. Whoopsies. So 48 breaks down into 6 and 8. 6 is 3 and 2. 8 is 4 and 2. And this is all multiplication. So it's not 4 and 4. 4 times 4 is 16. This is 4 times 2, which is 8. And then it breaks down further. I'm going to write them all out. I have a 3, a 2, the 2 2's that came from the 4 and the other 2 over here. How many pairs do you have? I notice 1 pair of 2's and even a second pair of 2's. So in the other problems, I had 1 pair of 5's and 1 pair of 3's. Well, in this particular case, I have 2's, but 2 pairs of them, and a leftover 3. What is 2 to the second power? 4. If you don't believe yourself or you think you did something wrong, type in the original, type in your answer. The decimals should be equivalent. Letter D, 12 breaks down into the following. So I see a 3, a 2, and a 2, a single pair of 2's with a leftover 3. Square root of 75. See, I think of 75 as 3 and 25. 25 is 5 and 5. So I have a 3, a 5, and a 5. 1 pair of 5's and a leftover 3. Please note the difference between, oops, never mind, they're different problems. Scratch that. Keep going. Square root of 200. I see 100 and 2. 100 breaks down into 10 and 10. If you want to keep going, you can. 10 breakdowns into 5 and 2. 10 breaks down into 5 and 2. I already recognize that I have a pair. So I'm kind of taking a shortcut, but I see that I have 1 pair of 10's and a leftover 2. Pretend for a second you didn't see that. Let's get it all the way down as low as it can go. 5 and 2, 5 and 2. So I'm going to write them all out. I have a 5 and a 5 and 1, 2, 3 2's. So I have a pair of 5's that's going to come out. I have a pair of 2's that's going to come out. And I have a leftover 2. There's multiplication in the middle here, just as there was multiplication every other place. 5 times 2 is 10, square root 2. So I did save myself a little bit of time if I would have stopped with these values and recognizing that, hey, there's my pair. A couple more. Letter G already has a number out in front. If you'd like, just forget about it for a second. Don't really scribble it out, just pretend it's not there. 32 breaks down to, let's see, 4 times 8, 2 and 2, 4 and 2, 2 and 2. Lots of 2's. 1, 2, 3, 4, 5 of them. 1, 2, 3, 4, 5. How many pairs of 2's do you have? 1, 2. So not only are there 2's, but there are 2 pairs of 2's. Well, remember that number I told you to scribble out? It's still really there with multiplication. So it's 2 times 4 square root 2, 8 square root 2. Holy moly, that was a long one. They don't get too much harder than that. Let's try letter H, the square root of 54. The square root of 54 I found breaks it down into 2 and 27, and I'm going to keep going. So yes, there's a negative 4 out in front. Just hang tight with it. All right, so the square root of 54 is really, in its simplest form, a 2, and it looks like 3 3's. Pairs, I have 1 pair of 3's. This 2 and this 3, I probably shouldn't circle them. That 2 and that 3 aren't pairs. They can't go anywhere. So I have a pair of 3's that comes out. This 2 and this 3 have to stay in, and you might as well call it a 6. That original 4, don't forget about it. It's easy to do. Negative 12, square root 6. That concludes today's lesson. Please let me know if you have questions. There's a lot of information. Don't be too overwhelmed. We'll talk about it in class. Thank you so much.